In the set of matrices, the similarity and equivalence notions appear in the discussions of diagonalizable matrices and eigenvalues. Essentially, this is what makes them worth much in linear algebra. Matrix similarity doesn't mean equality of matrices. Instead, similar matrices share some common important properties and aspects, such as common ranks and determinants. Watch these two transformations. The one on the left squishes the plane into a line, so the output is in 1D, while the output of the one on the right is still in 2D. These two matrices have different ranks since they produce outputs in different dimensions. We can securely now say that these two matrices aren't similar. To grasp the idea more, we need to take a look at the very definition of matrix similarity. However, we'll need to have a good understanding of the essence of matrix multiplication. If you haven't watched the video on the applications of matrices, definitely pause and have a look at it. Two matrices are similar when an invertible matrix P exists and satisfies this equation. Let's understand the intuition behind that. You should think about the matrix A as a linear transformation and about the matrix P and its inverse as a change of basis. With that being said, this means if A is similar to B, then we can get the matrix B when we express the matrix A in another basis. Consider this example now. These two matrices are similar since an invertible matrix P can be found such that this is satisfied. By visualizing the effect of matrix B, we can see that this transformation stretches the I and j hat as well as the unit square. We can see also the change in determinant. Well, keep a record of that picture in your brain. We're gonna come back to it later. Now, we said that P acts as a change of basis. Here, P transformed the I and j hat to the vectors 2, -2 and 0, 1. I'm gonna remove the grids to make the picture nicer. Now, after applying the matrix A that is similar to the matrix B to this result, we get this. The last step now is to apply the matrix P inverse to this result. Compare the two outputs now. That's pretty cool, no? They are the same. What this essentially means is that similar matrices correspond to the same linear transformations, but in different coordinate systems. Now let's jump to matrix equivalence. By definition, A is equivalent to B if there exist P and Q invertible matrices such that this equation is verified. Interestingly, matrix similarity and equivalence have to do with each others. That is, if A is similar to B, then they are necessarily equivalent, but the converse isn't true. The way I like to think about matrix equivalence is by appealing to row-column operations. A nice way of putting it is that A is equivalent to B if and only if A can be obtained from B by means of column or row operations. The row-column operations are the following: flipping two rows or columns, scaling a row or column by a constant, and adding a multiple of one row or column to another. For instance, these two matrices are equivalent, since if we add -1 times column 2 to column 1, we get this matrix. Now, flipping the rows, we get this one. So we started with a matrix and we reached the other by means of row and column operations, which means they are equivalent. In fact, this has a special geometric meaning. If A is equivalent to B, we have this relation. In matrix multiplication, we consider the multiplication from the left by an invertible matrix, of course, as row operations on the matrix, and the multiplication from the right as column operations on the matrix. Let's get back to these two matrices. We said that we need to apply -1 column 2 plus column 1. This corresponds to this multiplication from the right. And flipping the rows corresponds to this multiplication from the left. These matrices are what we will call in the coming videos the elementary matrices. Let's visualize that now. This is the output of the transformation corresponding to the matrix B. On the other side, applying the three matrices Q, A, and P respectively, we get this output, which is exactly as that of B, isn't it? For more interesting topics about linear algebra, feel free to check these videos. For more about matrices, stay tuned. Thanks for watching and don't forget to hit the like and subscribe buttons.